Thanks for tuning in. So where did we end last time was with this I del bar lemma. So it was a sort of interesting lemma, which was a bridge between the real and the complex worlds. So it says that if you've got a closed and real valued 2 form on a complex manifold, now a 2 form is living inside the complexified 2 forms, and the complexified 2 forms breaks up as this direct sum. So you could, in principle, have components here, here, and here. But we are told in the beginning, we're assuming that it's over here. And now we're saying, so suppose you've got a 2 form that's living over here, which is closed and real valued. So it came from an underlying real valued 2 form. Then the claim is that anything like that can be written as a sort of a double derivative of this form. So it's I del bar phi for some real valued function phi. Okay. And we gave this proof. And this proof sort of didn't rely on a sort of local coordinates. It was more just sort of canonical. But I thought it's a good idea then to start here by just going through the similar calculation, but just writing things out in local coordinates. So, so suppose you've got an alpha like this. So you're starting off with a real valued smooth function on an open set U, and then you calculate this double derivative here, I or del bar phi. Well, what's it going to look like? Well, let's have a look here. So start off by choosing local holomorphic coordinates, zi's, on U, so you can always express that in terms of the real and imaginary parts. So then you can calculate this del bar phi in this way. So it's going to be the sum of the derivatives of phi with respect to the z bar k's, because this phi here is going to be a function of all the z's and all the z bars, some arbitrary smooth function. And then I calculate del of this. So that means I've got to sum over the derivatives with respect to the z's, which is what I'm doing here, times the dz's or the dz's. So this is what alpha is looking like when I write it like this. That's what it's looking like locally. And of course, it's a little bit confusing here because I've written it down using complex coordinates, but we did start with a full-on real value 2 form, right? So if we want to think of this in a completely real way, then we'd want to write it not in terms of complex coordinates, but in terms of real coordinates. So let's just do that. So the first thing to remember is that z is x plus iy. So I can write these dz's as dx's plus I dy's. And the dz bar will be then dx minus I dy for that particular coordinate. So that I want to now write things in terms of the dx's and the dy's. And similarly, when I differentiate with respect to z, then it's the same as this combination of derivatives in the x and y directions. And then I differentiate with respect to z bar, it's the same as this combination of derivatives in the x and y directions. We know that because this guy eats up this guy to give you 1. That's the reason for this formula, right? So that this will eat this to give 1. I should have said here dzj equals a half or del xj plus I del yj and so on. Okay. So I can calculate what this means here, this derivative here. I can write it in terms of the real variables x and y. So that's what I'm doing here. And I can multiply that out. So I'm going to get this as its real part, and then this as its imaginary part. So this thing here is a complex function, but it has a real imaginary components, and here they are. And so let's just call this real component here phi jk, and the complex component, let's call it psi jk. notice here that phi symmetric function, because if I replace j with k, then this guy is symmetric, and similarly this guy is symmetric. Whereas psi, which is this part here times a quarter, is anti-symmetric, because if I replace j with k, then I'm going to let's see. Well, if I replace j with k, then, for example, over here, I'm differentiating with respect to yj and then xk, which is this term here, and it's got the minus sign in front. So that's how the psi is anti-symmetric. So the phi is a real valued function, and all these phi j's are real, right? And so they involve the derivative of a real valued function with respect to its real variables, but these components do satisfy these symmetry relations. So if I want to write this whole thing out now in terms of the real geometry, then I would want to express this in terms of this, and then this in terms of this, which I now do. Right? So the dz, which dz bar, I can write in terms of the dx's and dy's like this. And then I just multiply that out. So finally, if I were to calculate this expression here, so I'm trying to understand what this formula means. It's originally expressed in terms of complex geometry, and I'd like to write it in terms of real coordinates. You just substitute in everything, and then you essentially get out something like this. So now it's a manifestly real. So this part's supposed to go away, but anyway, this is the real. This is what it looks like over there. So it's a manifestly real two form. Yeah. So the fundamental thing that I just wanted to stress here is this sort of calculation that if I have z equals, or we know that I can always write z as x plus iy. Those are the real and imaginary components of a complex variable. Then if we have a thing like this, what does this mean? Dz wedge dz bar. It means then dx plus I dy wedge dx minus I dy. And if I multiply that out, I'm going to get 2i minus 2i dx wedge dy. Okay, so whenever you see this expression, don't be afraid. It really just stands for this expression. This is actually a sort of, yeah. Okay, I always like to know what's the underlying real thing, just so that I can be reassured, because these guys are sort of easier to understand geometrically. They're one forms, they measure tangent vectors. These are slightly formal things, but they're not that formal. Like this guy measures the change in this complex variable which is a complex function on the manifold. Yeah. Okay, let's skip that. So that was just to see how it looks like in local coordinates. Now let's go to the next section in the Flock's books on Kähler manifolds. Okay, so here's some cool geometry now. So we're going to mix the concept of complex geometry with Riemannian geometry. And that's what Kähler manifolds do, and that's really nice. So suppose you have a complex manifold. And what does that mean? You can either think of it in terms of an atlas, or you can think of it in terms of an integrable, almost complex structure. Right? That's the way that I'm going to think of it right now. So that means on each tangent space, we've got this operator J, which squares to the minus identity. Okay, that's the way I'm thinking about this complex manifold. Each tangent space, I've got this linear operator, which squares to minus the identity. So it sends vector v to jv, and then if I do it again, I'll get minus v. Of course, I've sort of drawn a little right angle there, but that was naughty because there's no way to measure angles yet on the tangent space. So I should actually get rid of that right angle. I mean, it might have been that JV would have been sort of something like this. All that matters is that when you do it twice, then you get minus V. But of course, if your surface is embedded in R3, like this one that I've drawn is sort of seemingly is, then there is this canonical almost complex structure where you do rotate by actual 90 degrees. Yeah. Okay, so that's what an almost complex structure is. Now let's mix that geometric structure with the structure of a Riemannian metric, which is a different structure you can have on a smooth manifold. So you might have seen this before, but if you haven't, I'm sort of defining it for you now. So recall that a Riemannian metric on a smooth manifold M is a smooth selection of an inner product on each tangent space. What does that mean? It means I've got a smooth section of the cotangent bundle tensored with itself. Because what would such a thing be? It would be at each point, it would be a covector tensor covector, or something living in the covector space, tensor the covector space would equivalently be something that takes a pair of vectors and spits out a number, right? And that would be what a bilinear map is on the tangent space. But to be an inner product, you also don't want it to be bilinear. Bilinear means a linear map from the tensor product, the vector space with itself into R. That just means that it's linear in each slot, right? Now, a bilinear map on a vector space into the ground field R is not the same thing as the inner product. Inner product demands more axioms on that, right? So the one axiom is that it needs to be symmetric. So G of V comma W must equal G of W comma V. And it must be positive definite, meaning that if you G of V comma V must be a non-negative real number, and in fact, it can only equal 0 when the input vector is 0. Yeah, so that's the axioms of inner product that you know and love already. And that's what a Riemannian metric is. It's literally just an inner product on the tangent space at each point of a manifold. A smooth selection of an inner product. What I mean by smooth, I mean a smooth section of this bundle. That just means if I express it locally, I've got smooth functions in terms of the local basis, right? Because locally, if x1 up to xm is a local coordinates, then anything like this, right? Anything that's living over here can be locally written like will be a linear combination of these guys, right? So I can put little g subscript rj's there in front. So that's what a metric looks like locally. And these here are smooth functions on the manifold. Not arbitrary smooth functions because they need to be symmetric. So grj must equal gji. And also, as a matrix, it needs to be positive definite. Okay. So just one important thing to bear in mind, and something that you know from the study of inner products, is that you can equivalently phrase positive definiteness in terms of non-degeneracy. So if you've got a bilinear map on a real vector space, which is a symmetric bilinear map, and is also non-negative in the sense that the bilinear map applied to V comma V is greater than or equal to 0 for all V, then the following are equivalent. Like, firstly, to say that it's non-degenerate, meaning that the bilinear map applied to V comma W equals 0 for all W, if and only if V is equal to 0. That's what non-degeneracy means. That's exactly the same thing as saying that the map because you've always got this map here, right? The map from V into V dual, which sends a vector V to the pairing of V with blank, right? And you want this to be a injective map. Of course, if V is finite dimensional, which is always the case for us, then being injective would imply that it's surjective as well. But the key thing is I want it to be injective, and that's exactly the same as this statement here, right? And then that's equivalent to saying that that the pairing is positive definite. So in other words, the only way that you can get the pairing of V with itself to be 0 is if you input the 0 vector. Okay, so that's you would have done something like that in your mathematical career, but it's a good exercise. So that's exercise 1. Yeah. I might have made some error at this point. So any questions or comments?
If you didn't spot any errors.
Okay.
Nothing from my side.
Thanks. Yeah, so where are we now? Good. So we want to speak about when you have now we've got 2 structures, the complex structure, or so I say an integral, almost complex structure J, and we've equivalently got this Riemannian metric G, and we want to say that they're compatible with each other. And the natural thing to say would be that J, which is a linear operator on the tangent space, should preserve the inner product, right? In other words, G, which is J, which is a linear operator on the tangent space, should preserve the inner product. In other words, the inner product of Jx with Jy should equal the inner product of x with y. So if you've got 2 vectors x and y, and then you hit them both with J, the inner product should be the same. Okay, so it's an isometric map. So that's what it means to say that the Riemannian metric is compatible with the complex structure. And so if you've got that situation, so if you've got a compatible Riemannian metric on an almost complex or on a complex manifold M, then you can define the associated fundamental form of the metric as a certain 2 form. So it's a 2 form on the manifold. So a 2 form is something which eats up 2 tangent vectors and spits out a number. And the way the number is going to spit out is just going to be the metric applied to Jx, y. Okay. So I've written down a formula for some mathematical structure living on the tangent spaces. I claim that it's a 2 form, and which we'll check in a second. But I also want to show you that it is this structure here is itself compatible with J. In other words, I want to prove that. So this is a beast which eats up 2 vectors and spits out a number. It's not just any old beast. It's an anti-symmetric beast. But what's important is that it is compatible with J as well. Because if I calculate omega of Jx, Jy, by definition, that's going to be G of J squared x, y. Because here's the definition here. Right? I've done something wrong here. Let's fix this. Omega of Jx, Jy is going to be, by definition, G of J applied to Jx, Jy. I think I was supposed to write that. On the other hand, J squared is minus the identity. So this guy here is minus the identity. And I can take that minus sign out by bilinearity. And then I can use the fact that G is compatible with J. In other words, G applied to these 2 vectors is the same as G applied to J of those 2 vectors. And then I've got another J squared, which is a minus sign, and I can bring it in front. So I get a plus again. So I've proved that this is equal to this. And of course, this over here is by definition omega of x, y. So just an important point there that once you've got your Riemannian metric, if your Riemannian metric is compatible with J, then its associated fundamental form will also be compatible with J. Okay. Now let's just check this statement that omega is actually, this fundamental form is actually a 1,1 form. So the first thing is I'm claiming that it's a certain kind of 2 form, namely a 1,1 form, but I should check that it is indeed a 2 form. The only thing I need to check is that it's antisymmetric, because a 2 form is a machine which eats up 2 vectors linearly in each slot and is antisymmetric in the slots. So I've got to calculate omega of y comma x and prove that it's equal to minus omega of x comma y. Right? So omega of y comma x is by definition this. And then g of these 2 vectors is the same as g of j applied to those 2 vectors, because g is compatible with j. And now I've got a j squared, so that I can replace it with minus 1. And I can take that minus sign out. And then this here is exactly the definition of omega of x comma y. So I proved that omega y comma x equals minus omega x comma y. So I do indeed have a 2 form. Is it a real 2 form? Well, yes, because what's its definition? Definition of the 2 form is simply this. So it's clear that it's real valued, because I started off with 2 vectors in the real tangent space. This is the real tangent space here. I have calculated a number which is real, because to calculate it, I just have to apply g, which is real value, to these 2 vectors, which are, again, in the tangent space. So it is a real 2 form, and it's not just any old 2 form. It's a 2 form which is of type 1, 1, right? Because the 2 forms split as type 2, 0, 1, 1, and 0, 2. It's actually going to be of type 1, 1. So let's check that. Okay, so if you want to check that if something is a 1, 1 form, what you need to check is that when you feed it to a pair of vectors of type, when you, what should I check here? I need to check that if I need to check that if I feed it a vector of type 1, 0 and another vector of type 1, 0, that I must get 0. In other words, it's only going to be non-zero potentially on vectors where I feed it a vector that's of type 1, 0, and then y must be of type 0, 1. Right? So I need to check 2 things, that if I feed it pair of vectors where each of them are of type 1, 0, then I want to get 0. And if each of them are type 0, 1, I want to get 0. So the only place where I can potentially get a non-zero answer is when I feed it a vector of type 1, 0 with a vector of type 0, 1. And that exactly is the statement that it's a 1, 1 form. I never quite proved that lemma, but that's sort of easy enough to prove and is in the flock quite early on. I hope you believe me on that, but that's sort of natural to see. So this is what I have to prove, these 2 properties. So let's prove property 1. So if I feed it a vector, each of them being of type 1, 0, then what does omega do? Well, firstly, one thing we do know is that no matter what vectors I feed it, omega satisfies this property here, right? Omega is compatible with J, as I showed a little bit earlier. Now, on the other hand, if my vectors are of type 1, 0, remember that actually means that they're living in the complexified space, then J applied to such a vector is I times such a vector. That's the definition of the 1, 0 space. It's the I plus I eigenspace for J. So that means that J applied to X is IX and J applied to Y is IY. That's the definition of being in the 1, 0 subspace. So this thing over here is equal to omega applied to Ix, Iy, because Jx equals Ix and Jy equals Iy. And then remember that this omega now, everything's been extended out linearly, so the I comes out and the other I comes out, so I get a minus in front. So on the one hand, I've calculated that this equals omega of x comma y, and now also calculated equals minus omega of x comma y. So the only conclusion we can draw is that applied to vectors of this form, omega must be 0, which is what I wanted to show. And then a similar argument would be for when I feed it two vectors of type 0, 1. It'll also vanish. So there, I'm done. I've proved that omega is a 1, 1 form. Right. One thing I want to point out here is that, so remember what we're doing, we started with a Riemannian metric G, and we asked that it be compatible with the complex structure. Then we got out this associated fundamental 2 form, omega. Now, the information of G and omega is sort of interchangeable. And you can start from the one perspective or from the other perspective. But right now, we started with a G, and then we have its associated omega. Omega is a 1, 1 form, but also G will be a tensor of type 1, 1, in the sense that as a 1, 1 tensor, G is a bilinear map on the tangent space at each point, and it will vanish when you feed it vectors of type 1, 0 and feed it two vectors of type 0, 1. By the similar reasoning, right? Exactly the same proof. Because I always have this equation, no matter what vectors I feed G. But if the x and y are eigenvectors of J with eigenvalue I, then the left-hand side is going to be minus the right-hand side. So that means that the left and the right-hand side must be 0. And similarly, if the left and right-hand side were eigenvectors with eigenvalue minus I. So the only way that you can get a non-zero answer is if I do with this guy's eigenvector with eigenvalue plus I, and this is an eigenvector with eigenvalue minus I, because then the I times the minus I will come out as a plus 1 in front. Then I'll just be saying that G of x comma y equals G of x comma y, so there's no contradiction anymore. So that's just to say that what the metric will look like locally in terms of the z and z bar coordinates. So if you've got a metric which is compatible with J, then it's going to have a certain form locally. So let's just write that out. So suppose you've got a complex manifold and you've got coordinates z1 up to zm. So if someone gives me a 1, 1 form on M, well, by definition, a 1, 1 form is going to be linear combinations of these forms here. I should have said dzj, which dzk. Okay, right? Because these are exactly, that's the definition of, well, not quite the definition, but it's a characterization of being a 1, 1 form. It means that you're linear combinations of these guys. Because the 2, 0 forms would be the things that have dzj, which dzk, those guys. And the 0, 2 forms would be the things that are dz bar j, wedge dz bar k. Okay, but when you've got a mixed wedge like this, then you're a 1, 1 form. So we know we can always write any 1, 1 form like this. And in fact, these coefficients here can be calculated by taking our 1, 1 form and applying it to these vectors here in the complexified tangent space. Now, omega applied to this pair of vectors. What is omega? By definition, it's G of J applied to the first vector, comma the second vector. This is how omega is defined, going from here to here. And by definition of what del Zj is, it's an eigenvector with eigenvalue I. So I can pull that I out in front. It's an eigenvector of J with eigenvalue I. So, and then I get out this thing here, and this here, which is the complexified metric applied to these vectors living in the complexified tangent space. We can call these numbers G, J, K, right? These are complex numbers. they will actually be real numbers. Actually, we'll see in a second. Why must they be real? So there'll be I times a real number, because why must that be the case? Because remember, dz wedge dz bar is, by a little calculation here, 2I dx wedge dy, right? So where am I? Here. So what I do know is that omega is a real two form, and so it has to then be expressed, when I express in terms of x's and y's, it has to have real coefficients in front. So this guy is going to be 2I or minus 2I times something involving dx and dy's. So that means that these numbers here have to be real imaginary. Sorry, what did I say? Purely imaginary, right? In order for omega to be a real value two form. Okay. Now I've confused myself, because that would seem to suggest that these guys have to be real. And does that make sense? I guess it must make sense. I'll come back to that after the break. Anyway, let's talk about this here. So this was how I was just trying to show you how the associated fundamental form of a Riemannian metric compatible with the complex structure looks like locally in terms of the z coordinates. It can be written like this. And again, I could write that in terms of the real components, real coordinates x and y's, using this expression. Similarly, for the metric itself, I know it can be written like this. Why? I know it's of type because it's a type 1,1 tensor, so it doesn't have 0, 0, 2, 0 and 0, 2 parts. So there's no parts like this, as we just saw earlier. Yeah. Now, let's just do this little calculation here, because I'm clearly getting confused. Let's just calculate this here. So this is, by definition, dxj plus I dyj tensor dxk minus I dyk. And if I write that all out, I'm going to get dxj. See, I don't have any, I can't now say that something is 0. I have to write it like this. Let me write it like this. Minus dyj tensor dyk plus I times dyj tensor dxk. And I think this is supposed to be a plus. Okay. I think what I wanted to say here is that these numbers here had to be Hermitian. So they, in other words, what I wanted to say was that these numbers here are complex numbers, but not any old complex numbers. They satisfy that if you transpose this matrix, then you should get out complex conjugate. But it's going to have to be a positive definite Hermitian matrix, I think, unless I'm we'll come back to this. I might be missing a factor of I here. Anyway, any comments there? Maybe you guys are picking up an error I'm making. Okay, so let's just recall where we are. We're starting with a almost complex manifold, and then we're introducing a Riemannian metric on it, which is compatible with the complex structure. And from that, we then got this fundamental form of the Riemannian metric. I haven't yet said what a Kähler manifold is. So to do that, I first of all have to remind you what a symplectic form is on a manifold, right? So a symplectic form on a smooth manifold is a two form satisfying two properties. Firstly, it has to be non-degenerate at each point. What does that mean? It means that if I consider it as a machine which takes in two tangent vectors and spits out a number, then that machine, when applied to x comma y, is 0 for all y if and only if x is 0. Right? That's the non-degeneracy condition. By the way, this is the same thing as saying that, so if your manifold is, say, this would automatically imply that the manifold has to be even dimensional. So if it has dimension 2m, then this is exactly the same thing as saying that the mth wedge of omega at m times, if the mth wedge of omega is non-zero. Okay, maybe that's a nice exercise as well. It's just got it's a purely pure linear algebra statement. The non-degeneracy of a bilinear form is equivalent to its top wedge being non-zero. And then secondly, it mustn't just be non-degenerate, it must also be closed. You see, this condition here is just a condition on the tangent space, and it's not a condition of how omega varies from point to point. Whereas this is a condition on how omega varies because it involves the derivatives of omega as you move the base point. Okay, so that's what a symplectic form is on a smooth manifold. I'm not talking about complex manifolds, just smooth manifolds. It's a non-degenerate closed two form on the manifold. Where does that come from? So you might wonder why would anyone ever care about something like this? Yeah, so Frank's got a question.
First thing with the exercise, I just wanted to clarify what is the statement?
Yeah, good question. Let's get some space here. So suppose you've got a vector space. Let's say it's a finite dimensional vector space. And you've got omega. Whoops. You've got an antisymmetric two form. I don't think it even needs to be antisymmetric for this thing, but let's make it. So it's an antisymmetric two form. So it's an element of the second wedge of the dual of V, right? So in other words, it eats into vectors in V and spits out a number in an antisymmetric way. So then you want to prove the following are equivalent. The first thing is that omega is non-degenerate What do I mean by that? I mean that if I think of omega as something as a machine which takes in two vectors in V and spits out a number, then that is 0 for all W if and only if the first vector is 0. Okay. And the other thing is like, so there, in this way of thinking, I'm thinking of omega as just a machine which takes in two vectors and spits out a number. But I could alternatively think of as omega as sort of living in a vector space of its own right, instead of thinking of it as a function and not, I think, what space does that function live in? It lives in its own vector space, which is this guy. And then I can say that the top exterior power of omega, so I take omega, so I've wedged it with itself here, m times. And what is m? M is half the dimension of V. It'll turn out, when you do this exercise, that V has to be even dimensional. So this guy here, where is this guy living, right? This guy is living inside the 2mth wedge of V star. And since, so that means that the dimension of V is 2m, right? So this, whenever I take the top, if I've got a vector space of a certain dimension and I take its, if the dimension of the vector space is n, and I take its nth exterior power, then you know that that new space is a one-dimensional vector space, right? The top exterior power of a vector space is one-dimensional. And this guy here is living inside that top exterior power. So it could either be 0 or it could be a non-zero element. And the claim is that it has to be non-zero. Yeah. Okay. Happy?
I'm happy. Thank you.
So that, anyway, that other way is a little more sophisticated way of saying it, which comes in sometimes, but this is the easier way of saying it. Good. So, by the way, I was just going to say, why do I care about symplectic forms and where do they feature? Their motivation came out of the study of classical mechanics. So, in the 18th and 19th centuries, people were trying to formalize, Newton's equations of motion in a nice mathematical way, and they found that, Hamilton found that the nicest way to phrase that is in terms of a Hamiltonian. So then you have position and conjugate momenta, and there's this sort of beautiful way of rephrasing Newtonian mechanics in terms of Hamiltonian mechanics. Newton's mechanics, i.e. Newton's second law, is a second order differential equation, right? Because force equals mass times acceleration. Acceleration is a second order differential equation. So it's a second order differential equation. Let's say I'm living in three-dimensional space. In three-dimensional space, so I've got a particle moving around in space, and it's got a certain force vector acting on it, which is telling me, therefore, what its acceleration on this particle is. And to solve for the trajectory of the particle over time, I've got to solve a second order differential equation because I know what the acceleration is at each point. So I've got a second order differential equation in R3. And Hamilton showed that you can rephrase this as a first order differential equation in R6. Okay, and then I've got to talk about position and conjugate momenta. And when you've rephrased it in terms of that, R6 is now called phase space, and it has a lot of elegant properties. And when you think of this mathematically, you'll realize that even dimensional manifold, this phase space, mathematically, if I think of it as some abstract manifold, it's not just any old abstract manifold. It has a canonical 2 form on it, which is the symplectic form. And it's the information of knowing what is the conjugate momenta to a certain coordinate. So if given the dx, it'll tell me what the associated dp is. And anyway, it's just a long story, but that mathematically can be encapsulated as this symplectic form. So the answer to the question, why do I care about symplectic forms on manifolds? The motivation is that it arose from the study of classical mechanics. Gave us a nice way to formulate classical mechanics on general manifolds. You need to, in order to do classical mechanics on a general manifold, you need to have a symplectic form on your manifold. Okay. Since then, although that was the beginnings of the subject, it turned out to have all sorts of implications in the wider geometry and differential geometry as well. So, and it's in that sense that we're encountering it today. So, where are we? We've started with an almost complex manifold, and we've got a compatible Riemannian metric on it. That means its fundamental form is going to be a two-form. And the question is, when will that two-form be a symplectic two-form? That means I need it to be non-degenerate and to be closed. Okay. Now, the fundamental form of a compatible Riemannian metric G is definitely non-degenerate. So I definitely satisfy this first property because the underlying metric is non-degenerate. And remember that the formula for omega is that it's defined in terms of the underlying Riemannian metric. And so it's fairly easy to see that from this formula, since the underlying Riemannian metric is non-degenerate, it's an inner product, right? That means that omega will be non-degenerate. So we easily get number one. Question is, so in order for omega to be a symplectic, the key property is number two. I need to know how this omega is varying as I move the underlying point P. And so that's the definition of a Kähler metric. That a compatible Riemannian metric G on a complex manifold M is called a Kähler metric if its fundamental form omega is closed. Okay, so in other words, and we say that a Kähler manifold is a complex manifold equipped with a Kähler metric. So it's the nicest kind of situation you can be in. I've got a complex manifold. I'm trying to put a Riemannian metric on it. Now, of course, I've got two sort of geometric structures. I want them to be compatible. So I want the complex structure to be an isometry of the tangent spaces. And in that situation, the other nice thing that I can ask is that the associated fundamental form is going to be closed. Okay. Now you might ask for a geometric interpretation of this condition because right now it's a little bit long-winded, right? In order to define whether a metric is Kähler, I say you've got to start with a complex manifold and you've got to put a Riemannian metric on it. And then you've got to calculate the associated fundamental form of that Riemannian metric, and you've got to check whether that fundamental form is closed. Couldn't I just phrase it directly in terms of G? Why do I have to go via omega? And indeed you can. So you can phrase this condition on the Riemannian metric G entirely in terms of M and J. Okay, and this is quite a nice little theorem. I'm not going to prove it. But it says that suppose you've got a complex manifold, and suppose you've got a Riemannian metric G on M, which is compatible with J. And when I say compatible, I should say sort of on each tangent space, because the full compatibility we would like is that the derivative of the fundamental form is closed. That's the true compatibility we'd like. So we're sort of halfway there when we say that it's compatible with J. So now let omega be the fundamental form of G, and the following are equivalent: that d omega equals naught. In other words, it's a Kähler metric. And number two says that the Levi-Civita connection, or the covariant derivative of J, using the Levi-Civita connection of the underlying Riemannian metric, is equal to 0. Okay, so that's a bit of a mouthful. Let's unpack what that means. The nicer way of, since I'm not going to prove this, I don't really have to get into this very much, but the nicer way of understanding this is not in terms of the connection, but in terms of the parallel transport. So what this is saying is that the parallel transport associated to the Riemannian metric is compatible with the complex structure. Okay. So I told you what a Riemannian metric is. but I didn't speak about what the parallel transport associated with Riemannian metric is. So whenever you have a Riemannian metric on a manifold, there's an associated thing called the Levi-Civita connection, and that is equivalent to the data of having a certain parallel transport operator. So what that means is that whenever I've got a curve in the underlying manifold, then I've got a way of taking tangent vectors and parallel transporting them along that curve. And that means I've got a linear map from the tangent space at the beginning to any other tangent space, right? There's this beautiful way of constructing this. I'm not going to go into this, but this is what you get whenever you have a Riemannian metric. And now what we're saying is that parallel transport should be compatible with with J. So I don't think I need gamma to be a geodesic here. So suppose I've got any path in the manifold from P to Q, then I've got the tangent space at P and the tangent space at Q, right? So you can imagine I would want the following diagram to commute. Namely, I can start with the tangent space at P. I can start with the vector there, for example, this vector here. And I can apply J to it. And then I can parallel transport that vector to get me into this tangent space. Or I can start with V, parallel transport along gamma to get a vector here, and then apply J to that. So I should have been a little bit more careful here. Instead of saying V here, I should have said the parallel transport along gamma applied to V. And this should have been J applied to the parallel transport along gamma applied to V. Okay, so it's this square that I'm wanting to commute. And that's then turns out to say that parallel transport is compatible with J, that's actually equivalent to saying that the exterior derivative of the fundamental two form of the Riemannian metric is 0. Yeah. That's a cool statement, and I think we can stop there and have a 10-minute break. Dario's got a question?
No, sorry, that was accidental. I'm good.
Okay, see you guys in 10 minutes. 2:55 or 3:05. Yeah, so welcome back. We're speaking about Kähler manifolds, and we arrived at this definition. A Kähler manifold is a complex manifold equipped with a Kähler metric. So it's a kind of Riemannian metric on the underlying smooth manifold, which gets along very nicely with the complex structure in two ways. Firstly, the metric preserves the almost complex structure J. So that's a condition on each tangent space that you can check on each tangent space separately. And then there's also a sort of local condition about how the metric evolves, how it changes from point to point. And that's also got to get along with the complex coordinates. So, and there's two ways to say it. You can either say you calculate the associated fundamental form of the metric, and that's got to be closed, so that its derivative has to be 0. Or you can say that you calculate the Levi-Civita connection of the Riemannian metric, or equivalently, you calculate its parallel transport along curves. And then what you want is that parallel transport preserves this J map. Okay. Parallel transport is compatible with the J map. Parallel transport of G, let me say that, of G is compatible with complex structure. Okay. So one thing to bear in mind about a Kähler manifold, an interesting fact, is that if you've got a Kähler manifold, then, well, of course, the fundamental form is always a 1-1 form. And whenever you have a 1-1 form, which is closed, I know it's closed because it's a Kähler manifold, then by that lemma that we did earlier, we can write it as I del del bar phi, right? So we started the lecture. So that's interesting. So the fundamental form, which is a certain 2 form on the manifold, can be expressed as the derivatives of just a single function phi. Okay. Someone's calling me. 1 second. Hello, I'm giving a lecture. Okay. Yeah, so what does that mean? It means if I think about the metric, then the metric can be written like this. Obviously, for any metric, I know the metric is always going to be a 1-1 tensor, so it can be written like this. This is what we were talking about earlier. And of course, by definition, these G's are what happens when you evaluate the tensor on the del Z's and the del Z bars. And G and omega are interchangeable, right? Because if you say that G, originally we started with G and then we derived omega by saying that omega of x comma y is by definition G of j x comma y. But we can equivalently then say that if I'd given omega, I could calculate G, because G of x comma y would then be the same as omega of x comma jy. I think that's correct. Because if I sub in jy here, then I get G of jx comma jy, which is the same as G of j comma y. Yeah. So what I'm saying is that these numbers here are calculated in terms of the fundamental form like this, which, since this is an eigenvector with eigenvalue minus I get this out. And I know what omega is, right? Omega is I del del bar phi. So I have to calculate del del bar phi and evaluate it on this. That just means I'm calculating the second derivative of phi with respect to zj and then z bar k. Okay, so that's what this number here is, then this number here. Yeah, so that's interesting. Why? Because usually when you have a Riemannian metric on a smooth manifold, then you can think of it as a matrix, right? and all the entries of the matrix are sort of independent functions, other than the fact that it has to be a symmetric matrix. Basically the entries of the matrix are independent. So that you on a two-dimensional manifold, you would have like 3 independent entries. But now we are constructing this Riemannian metric just from a single function, or shall I say, we start with from some single master function phi, and then we define the metric just by the second derivatives of phi. So you can see what a major simplification that is. So a Kähler metric is a much simpler object than just a random Riemannian metric. It is all boils down to this phi, which is called the Kähler potential. So that's, although the phi is not globally defined, it's only locally defined. It's useful to know that locally you do have this phi, which you can express the G just in terms of the derivatives of phi. Okay, so a Kähler metric is constructed locally from a single smooth function, whereas usually a Riemannian metric is constructed locally from several independent functions. Okay, so at the moment, what have we got? We started with a complex manifold, and then we defined a Riemannian metric, and we said that we said that a Riemannian metric is Kähler if it's compatible with the complex structure in the sense, firstly, on each tangent space, you want this to hold, and then you also want the local condition that the associated fundamental form is closed, which is telling you how G is varying locally. You can have an alternative point of view, which is to start with a symplectic manifold, and then you would want to introduce a complex structure. So how would you introduce a complex structure? You would introduce an almost complex structure on each tangent space, and you'd want that to be integrable. And then you'd want the omega to be compatible with the almost complex structure J, in the sense of this equation. Okay, so that's a nice exercise, is to check that if you do it that way, so you're starting with the structure of a symplectic manifold, no complex structure, you just start with a symplectic manifold, then you try and introduce a J which is compatible with the omega in this sense, then you could define a Riemannian metric like this. So the claim is that that will actually be a Riemannian metric, so it's going to be an inner product on each tangent space, and it's going to be compatible with omega in this sense here. So that's what the exercise is about. So in summary, a Kähler manifold is really a 4-tuple consisting of underlying smooth manifold M, an almost complex structure on M, a Riemannian metric on M, and a 2-form on M. And they're not, and where all this data is compatible with each other, in the sense that firstly, J has to be integrable, not just any old almost complex structure. I want it to be an integrable almost complex structure, so that this guy is actually a complex manifold and not just an almost complex manifold. Then I want G to be compatible with J and omega, right? Because this to be compatible with J is this requirement here. To be compatible with omega is this requirement here. And since you're satisfying this requirement, then automatically you know that the fundamental form is closed, because I said that that omega has to be a symplectic form. Yeah, so that's the third condition, that this omega is a symplectic form which is compatible with J and G. So it's like it's one of these situations in maths where, you know, any 2 of these determine the third one. So you've got this structure, and this structure. And given J and G, we get omega. Given J and omega, we get G, and actually given omega and G, we get J. So, but if you want to state the definition in the most symmetric way, then you'd state it this way. But if you want to state it in a minimalist way, then you just start with 2 of them and you define the third one out of that. Okay, so let's give some examples of Kähler manifolds. So if you like complex geometry and you like Riemannian geometry, then you'll like Kähler manifolds, because that's where you have a complex manifold and a Riemannian metric. So just to carry on, our favorite example, or my favorite example of a complex manifold is again a Riemann surface, but especially just these surfaces embedded in R3. Those are nice examples of surfaces because we can visualize them very easily. And every such embedded surface in R3 naturally inherits the Riemannian metric from the ambient space, right? Because you've got your manifold M, and so each tangent space is actually a subspace of R3, and R3 has the Euclidean metric on it, right? The standard Euclidean inner product on R3. So we can just restrict that inner product to this plane, and so that means we've got a natural way to associate an inner product to each tangent space. So whenever you've got an embedded manifold embedded inside some Rn, then you always have this inner product. In fact, every manifold can be embedded in Rn for n big enough, so that's one way of seeing that every manifold admits a Riemannian metric. So since I've got, on the other hand, so I've got a natural candidate for what the metric should be on these surfaces. And of course, we already know what the complex structure is on these surfaces. Because we've got this tangent space, we've got a natural way of rotating counterclockwise by 90 degrees. Counterclockwise, I know what that means since it's an oriented surface. So on these surfaces embedded in R3, we naturally have this data that I'm looking for. I've got the almost complex structure, which is actually integrable, as we saw last time, and I've got a Riemannian metric. So the question is the Riemannian metric compatible with the complex structure? And yes, that's true, because this map J, what do we want it to be? We want it to be an isometry. And that is true because if I rotate by 90 degrees, then it preserves all inner products, right? So J is an isometry, so that this guy here is indeed compatible with J. The other thing I have to check is that its associated fundamental form is closed, right? The fundamental form of this G is going to be a 2 form on the manifold. And that 2 form has to be closed because its derivative will be a 3 form, and you don't have a 3 form. You don't have a non-zero 3 form on a 2-dimensional manifold. Okay, so it's just closed for dimensional reasons. So there we go. Every 2-dimensional complex manifold, or every 1-dimensional complex manifold can be equipped with a Kähler metric, but in particular, if the manifold arises as the complex manifold associated to a embedded surface in R3, then everything can be thought of very geometrically. It's just the underlying Riemannian metric or the ambient metric and the ambient complex structure. So you know that my favorite complex manifold is the 2-sphere. So let's work this out all explicitly for the 2-sphere. Say in the theta phi coordinate system. Okay, so here's the 2-sphere. And I've got coordinates on it given by latitude, which is theta, and longitude, which is phi. All right, so then I've got it. Obviously, this doesn't cover the whole sphere, but it covers the sphere away from the north and south poles. And this coordinate chart. And here's a point P. And notice where the coordinate tangent vectors go, right? Del theta goes down because remember del theta is the vector associated to increasing theta and leaving the other coordinates fixed. So when I increase theta and I'm sitting over here, then I'm going to be going down. And if I'm sitting over here and I increase phi, then I'm going to be going to the right. Okay, so there's del theta and del phi. They have basis for the tangent space. And I'd like to write things in terms of these coordinates, because these are the coordinates we know and love for S2. So let's first of all just write out what those tangent vectors are. So this point P can be described parametrically like this, as we know, because its Z coordinate will be cosine of theta, while its X and Y coordinates will be sine of theta cos phi and sine of theta sine phi, respectively. So if you think about it, that means when I'm trying to calculate what the vector, for example, del theta is, this vector here, I have to take an equivalence class of a curve we are just changing theta and not changing phi. And then I'm going to do the equivalence class is specified by the derivative of that curve with respect to t, at t equals 0, right? So you might as well just differentiate this parametric function p with respect to theta. So in other words, this vector here is literally just the derivative of p with respect to theta, which I can calculate, and I get this. But the derivative of this with respect to theta is cos theta, sine cos phi here, and derivative of cos theta is minus sine theta. Okay, so this vector here is that vector over there living inside R3. Okay, and similarly, I can calculate del phi, which is this vector here, by just differentiating p with respect to phi. So this formula here, which is calculated by differentiating this with respect to phi, is going to be this vector here. Note that it's got 0 in the z component because these vectors here are going around the sphere at a constant height, so they don't have a z component. Right? Because here z, x, and y, so they don't have a z component. They're flat. They're sort of flat. Good. Where are we? We're trying to understand the two-sphere as a Kähler manifold. That means I need to understand it as a complex manifold, and I need to understand it as a Riemannian manifold. Okay, as a Riemannian manifold, let's understand it. Well, I need to understand the inner product. So I know what the inner product is abstractly. It's just the inner product in R3 restricted to each tangent space. But I would like to express it in terms of these theta and phi coordinates. In other words, I need to calculate the inner product of these coordinate vectors with themselves. So let's do that. If I calculate the inner product of this vector with itself, how do I do that? Well, I'm just using the underlying inner product in R3. So it's literally just the dot product of this vector with itself. If I do that, I think you'll agree that I'm going to get a cos squared theta, cos squared phi, plus cos squared theta sine squared phi. So I'm going to take cos squared phi plus sine squared phi gives me 1. So I get cos squared theta plus sine squared theta, which is 1. So I'll get this. Similarly, the inner product of del theta with del phi is 0, because this dotted with this is 0. You also see that from the picture. These guys are orthogonal to each other. And similarly, g phi phi, let's calculate it. I have to take the dot product of this with itself. So I'm going to get sine squared theta sine squared phi plus sine squared theta cos squared phi. So that's going to be sine squared theta. Okay, so as a matrix, I can write the metric like this. Okay, good. So far I'm just doing Riemannian geometry on the two-sphere, and I've written out the metric in terms of the theta phi coordinates, the latitude and longitude coordinates. What about the complex structure? Well, how does the complex structure work? We agreed that the complex structure would be rotating each vector in the tangent space by 90 degrees counterclockwise. How do I rotate by 90 degrees? Well, I should sort of get an orthonormal basis for the tangent space, and then I just take the one basis vector, push it into the other basis vector, right? But I've got to orthonormalize my basis. I can't just send d theta to d phi because I don't know whether these are yet normalized. Maybe this guy's got a different length to that guy. I don't want to change the length when I rotate. So I should find an orthonormal basis for my tangent space. So that means I should divide by the norm of the vectors. And if you look at these vectors here, del theta has got norm 1, so that's not a problem. But del phi has got norm sine theta. That's the norm squared over there. So when I divide by sine theta, then I will get out an orthonormal vector. Okay, so all I'm saying is that this guy's got norm 1, but this guy doesn't have norm 1, as you can see, because as you move it up, it's going to get smaller and smaller, whereas we'd want it to say have the same size to our normal. Okay, so in order to counteract that, I need to divide by sine theta, which will have the effect of making the del phi bigger. Okay, so now how does the complex structure work? It's going to map the orthonormal basis vector E theta to the orthonormal basis vector E phi, right? Because it's going to take this guy to that guy once they've been normalized. And then this guy, when I rotate by 90 degrees, is going to get mapped to minus E theta. Okay. So if I want to write that in terms of my coordinate vectors, this is how the complex structure looks like in terms of the coordinate vectors. Okay, if I want to write that as a matrix, I could. But then I would be saying that as a matrix, J, when I act on del phi, I'm going to get, so that's del theta, del phi. So the first coordinate is 0, and the next coordinate is 1 over sine theta. And when I act on del phi, I get minus sine theta, 0. Yeah. Notice that J squared equals minus the identity. Good. So now I've written down the Riemannian metric structure locally in this coordinate system. I've written down the complex structure locally in this coordinate system. I know that they're compatible, so everything is all good. But let's just carry on working out the other data that we would normally work out. So for example, the fundamental form of G, what is that? I'm supposed to calculate omega, which is the fundamental form. Remember, it's calculated as J of x comma y. So let's calculate that. So I know it's going to be ultimately expressed as d theta something times d theta wedge d phi, because that's the only two form I can have, right? I can't have a d theta wedge d theta, and I can't have a d phi wedge d phi. Where this number in front is going to be calculated as g applied to j of del theta comma del phi. That's the definition. And j of del theta, we agreed that j of del theta is del phi over sine theta. So I've got to calculate that. Sine theta comes out, and g of del phi with del phi is sine squared theta, so I get sine theta out. So in other words, my fundamental form of the Riemannian metric is going to be sine theta, d theta, wedge d phi in these theta phi coordinates. Now, what is interesting about this 2 form? Well, if you think about it, it's the underlying area 2 form of the 2 sphere. Why is that? One way to see at least that you're on the right track here is because if I integrate it over the 2 sphere, I will actually get the area of the 2 sphere. So how do I integrate over the 2 form over the 2 sphere? I just parameterize my 2 sphere, and then I just sort of remove the wedge symbol. So to parameterize the 2 sphere, the theta coordinate's got to run from 0 to pi, and the phi coordinate's got to run from 0 to 2 pi. So if I'm integrating omega over the 2 sphere, what that boils down to is calculating this ordinary integral. This is an ordinary double integral, right? How do I calculate that? Well, the phi integral I can immediately do to give me 2 pi. I've got to integrate sine theta from 0 to pi, and that's going to give me 2. So the integral of this 2 form over the 2 sphere is 4 pi. And that's the indication that it is the area form. Alternatively, I can just go ahead and calculate what the standard area form is on S2 in terms of theta phi coordinates, and you'll get this. Okay. Any questions there? You want to be able to mix and match in your head between working with Zs and working with X's and Y's. In other words, writing things down in terms of complex coordinates and writing things down in terms of real coordinates. So here is how things look like in terms of the theta and phi coordinates. Notice that theta and phi are not the underlying real coordinates of the complex coordinates, right? I do have a z coordinate on my two-sphere, which we'll go into in a second, but theta and phi aren't the real and imaginary parts of z. They're rather just some nice sort of coordinates that I like to have on the two-sphere, but they're not actually the real and imaginary parts of the holomorphic chart. But let's write omega in terms of those holomorphic coordinates now, just so that we can translate between the two pictures. So what are the holomorphic coordinates on the two-sphere? Well, remember, we use stereographic projection, and actually we want to stereographically project from the south pole. So it turns out then that if you've got a point that's got an angle theta, and when you stereographically project from the south pole, that point there where it crosses the xy plane will be given by this formula in terms of theta and phi. I think that was the exercise in the first lecture. If not, you should do it as an exercise. Okay. So that enables us to translate from the theta phi coordinates into our holomorphic coordinates. So I want to now take everything that I've written down before, like for example this fundamental two form, and write it in terms of z's. So I want to write it in terms of dz with dz bar. So if this is my z, then this would be my dz, because I know how to calculate the d of something. I just differentiate it with respect to the coordinates. So I differentiate this with respect to theta, then I put a d theta. And then I differentiate it with respect to phi, and I put a d phi. So that's what dz would be. Since I've got dz, I know what dz bar is. I just take everywhere I see a plus I, replace with a minus I. So dz wedge, dz bar would be this. I just took dz and I wedged it with dz bar. And now let's multiply that out. So the d theta wedge, the d theta is going to be 0. So the only term I have to worry about is this times this. And equivalently, I'll get the same when I do this times this. So I'm going to get minus. I don't know why I said minus 2i here. That seems a little bit wrong. I've got a half here. That came from differentiating the half in front here. So I think I can eliminate this 2. Okay, good. So that's what dz wedge dz bar is. And of course, I can write it like this, because sec squared is 1 over cos squared. And so, on the other hand, I've got this half angle formula for tan, so I can write tan as sine over 1 plus cos. And now I recognize this little section here as being my two-form omega, my fundamental form, right? I calculated omega earlier. Here it is here. Right now I'm calculating dz wedge dz bar, because I want to phrase things in terms of dz wedge dz bar. And I found that dz wedge d bar basically looked at a part that looked like omega in it. So I could solve for omega here, and then I should get this expression here. And I think I've now got to put a 2i in front there. Okay, I hope you guys agree with me. I might have made a mistake here. If so, point it out. So I've expressed my fundamental form in terms of the z coordinates. Well, not quite, but I'm halfway there. I've written my fundamental form as this thing times dz wedge dz bar. And of course, I'd like to write this in terms of z as well. So then I've got it completely expressed in terms of z. Well, by just a little trig manipulation here, you can write this as this. I think I've now got to do something like a over 2 here. And now this expression here, what is it? Well, let's have a look. So I claim that this is 1 over 1 plus z bar squared squared. Why is that the case? Because here's the definition of z. And so if its modulus would then be tan of theta over 2. So its modulus squared would be tan squared theta over 2. 1 plus tan squared theta over 2 is sec squared theta over 2. And 1 over sec squared is cos squared. So this here is the same as this, basically. Up to a factor of 2 or something, which I might have missed. So the conclusion is that my fundamental form, which was originally expressed like this, in terms of the real coordinates or the theta phi coordinates, could be expressed in terms of the holomorphic coordinates like this. If I want to express it in terms of the real and imaginary components of those holomorphic coordinates, then you'd get something like this, right? Because z is x plus iy. So this can be written like this. But for now, let's just look at this formula here. Remember that I promised that the omega could be written as I del del bar of some smooth function phi. What would that smooth function be? Well, we can see that it has to be this function here. Because if I were to take this function and calculate del del bar of it, then I would get this expression, right? Because it's the first derivative is going to give me the 1 over 1 plus z bar squared times a z, and then the next derivative is going to get rid of the z. Let's just, I hope you agree with me, let's just do that little calculation quickly. Right, so I want to calculate I del del bar of log 1 plus z squared. Now z squared is z bar, right? So let's do that. I'm going to get I del, when I do this del bar, I've got to differentiate this with respect to z bar. When I do that, I get 1 over 1 plus z bar by the chain rule times the derivative of the inside with respect to z bar. And that's going to give me a z. So I get a z there, and then I get a dz bar. Okay. Now I've got to differentiate it again. Now differentiate with respect to z. So I get I times, let's do our little calculation. It's a now a product rule calculation. So it's bottom differentiate the top minus the top differentiate the bottom over the bottom squared. So it's the bottom differentiate the top with respect to z. It's going to give me 1. So then I'm going to get a dz wedge dz bar out. That minus the top differentiate the bottom. So let me put it here. So I get 1 with bottom differentiate the top. So let's write that out. 1 plus z bar squared times 1 minus the top differentiate the bottom. I'm going to differentiate the bottom with respect to z now. So then I'm going to get z times z bar. Okay, so I get out let me write like this. I get a dz plus the other thing would be I have a dz bar in it. And I don't care about the dz bar because it's not going to matter when I wedge it with the dz bar. Right? So in other words, it's only this term that that's going to matter. What am I saying here? I think I'm talking nonsense. Excuse me. So this is the bottom differentiate the top, minus the top differentiate the bottom, give me this. And so can I, bottom differentiate the top would be a 1 there, minus the top differentiate the bottom will give me that. So I get this cancels, right? Okay, which is what I wanted. Okay, so I've shown that indeed it's true that my fundamental form can locally be written like this as I del bar of something, and indeed that function is this function here. This function is not defined everywhere on the manifold, it's just defined in this chart. Okay. So all I was demonstrating here is that integral that I was calculating with respect to theta phi, I could also calculate with respect to x and y as well. So that's just to say that when you see something like this and you have to integrate it, you should always remember what does that mean? It means you're actually integrating this. And this guy I know how to integrate. Okay, so just in case you're anything like me and you get confused when someone asks you to integrate something like this over the complex plane, for example, what does that mean? It really means integrating this over R2, which is something we know what that means. Okay, I'll skip that. Let's carry on. So we understand now one nice class of examples of Kähler manifolds. S2 was our nice example, but now remember that as a complex manifold, S2 is the same as CP1. I spent a lot of time at the beginning explaining that. So now that I've expressed everything in terms of the z and z bar coordinates, I could then just write it in terms of the CP1. So now, in other words, I've written down what G is and what omega is in terms of the z coordinates. So this way I could then naturally generalize to CPN. So I know, so CPN is a complex manifold, and now I'm telling you what the associated Riemannian metric is, because it's the Riemannian metric whose associated 2 form is given by this expression here. But now instead of this phi, I must just change my phi by summing over a slightly different formula now when you've got more than one z in the game. Okay, but so there's just a natural way then you can write down a Riemannian metric on CPN, and you can express it in terms of the z coordinates. So that's just to say that CPN is a nice example of a Kähler manifold as well. Just take the same structure that I've written down for CP1 and naturally extends to CPN. Details are in the flock. Okay, but that's in a sense our most important example of a Kähler manifold, because that implies, for example, if you've got a submanifold of CPN, then it's going to inherit that Kähler metric. So we already came up with nice examples of submanifolds of CPN, these ones that were given by solution sets to a bunch of equations. So therefore, we've got a huge bunch of examples of Kähler manifolds now. Any complex submanifold of CPN will be a Kähler manifold. Just one more easy example, just the complex plane itself with the standard complex structure, right? The complex plane is a complex manifold, obviously. You can just take the Euclidean metric on G to be the Kähler metric, the Euclidean metric on R2, and clearly that is going to be a Kähler metric because it's compatible with the complex structure, again, because J is an isometric map, so J is rotating by 90 degrees, and that preserves the inner products. And also, if I calculate the associated fundamental form, I'm just going to get this. And that is clearly closed. Because if I calculate its D, I would have a 3 form, and that's impossible. You can't have a 3 form on R2. But it's nice to just see explicitly what it is, right? It's dx wedge dy. So here we see something interesting, which we saw in the case of the 2-sphere and in the case of R2, which is that the symplectic form seems to be giving you some kind of an area form. So we'll talk about that in a second, and I'll end with that. But firstly, I just want to write out what this is in terms of the Z and Z bar coordinates. So once again, I claim that this thing here, which is sort of the natural 2 form you can write down on R2, can be expressed in terms of Z and Z bar like this. Why? Because dz is dx plus r dy, dz bar is dx minus r dy, so if I multiply it out, I get this, and I'm multiplying by the I over 2 in front gives me that. So whenever you see something like this, don't be scared. It just means that. But it's just a convenient notation if you're wanting to do calculations in complex coordinates. Okay. Of course, since it's a 1-1 form, I'm supposed to be able to write it as I del bar phi for some smooth function phi. What is that smooth function? It's this function here. It's a half times the modulus of z squared. Note that this is a smooth function. It's not a holomorphic function. How do I know it's not holomorphic? Because it depends on z and z bar. Whenever you've got a function whose algebraic expression depends on z and z bar, then it's not holomorphic, but at least it is a smooth function, right? It is a real valued smooth function. It's just the length of a vector times a half squared. Length squared times a half. So if I calculate this double derivative here, what would it be? Well, the first derivative, the del bar phi, I would have to differentiate this with respect to z bar, which is going to give me a z. So I'm going to get a z times dz bar when I calculate this expression here. And then I've got to take the del of that. So that means I'm going to differentiate this with respect to z and then wedge it with a dz. Differentiate it with respect to z, I get a 1. So I get this out. So this expression is equal to I over 2 times dz wedge dz bar. So in other words, it's true what I was claiming, namely it is true that omega is equal to I del bar phi. Because this here, dx wedge dy, is equal to I over 2 dz wedge dz bar. Okay, so similarly on R to the 2m, which I can think of it as m copies of complex space, the same formula would then give me a Kähler form on Cm, right? So I could write it in terms of the real coordinates. Instead of dx wedge dy, I'm now going to have dx1 wedge dy1 plus dot 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 plus dxm wedge dym. That's my Kähler form as a 2 form. And I can write it like this if I want to, but now phi is just going to be the sum of the norm squares of each of the z's. Okay, so that's, in a sense, the most basic case of a higher dimensional Kähler manifold would just be Cm with this Kähler form. And the metric is just the Euclidean metric on R to 2m. Okay, so I don't think I'm going to have time to do this, but it's just a small calculation. I think I will put it in the notes, and you'll see it in the notes, but it's just the calculation to show following, namely, the question might be entering your head at this point, which arose from looking at that 2-sphere. So remember, when we looked at the 2-sphere, we calculated, so we had this Riemannian metric, and then we had the associated complex structure, but once we had the Riemannian metric, we calculated the associated fundamental form, and the fundamental form was something that we've already seen before when we were working with two spheres. It's the area form on the two spheres. It's the thing which, when you integrate, it gives the area. Integrate it over the whole of the two sphere, then you get the area of the whole of the two sphere. If you integrate it over a little region of a two sphere, then you get the area of that region. So that then would lead us to ask the question, hold on, is that always going to be the case? So is the, how do we generalize this? So let's talk about that. So if I've got a m-dimensional, or let's say 2m-dimensional Riemannian manifold, say symplectic manifold, then I'm going to get a top exterior form. I'm going to get a volume form. So I can define this guy. So it's the volume form of the symplectic form. What is that? It's a top dimensional form on the manifold, right? The manifold is 2m dimensional, so the top exterior power of the cotangent spaces stops at 2m. How do I define it? Well, by definition, I just take omega, which is a 2 form, and I take its mth wedge with itself. And then I divide by m factorial. Okay. That's called the Liouville form of the symplectic form. And it's an element in the top exterior power of the cotangent space at each point. And it's actually non-zero. Why is it non-zero at each point? Because we agreed earlier, it was the exercise, that this guy being non-zero is equivalent to saying that omega is non-degenerate. Since I have a symplectic form, it is non-degenerate. Okay. So I've got this thing which is non-zero, and it's an element of the top exterior power at each point. So in other words, it's a way to measure volumes at each point in the manifold. So it's something that you can integrate over the manifold itself. That's why it's called a volume form. On the other hand, if I have any manifold M, let's again say it's 2m dimensional, but could be of any dimension, doesn't have to be even dimensional, then I've got a Riemannian manifold. So G is a Riemannian metric. Then I'll also get a volume form, which I'll write as the volume form of the metric, vol G. It's again going to be a 2m form, top dimensional form. It's also going to be non-zero at each point. That's the definition of being a volume form. And how do I calculate this? Well, what I do is the P be an element of M, and then I'm going to find an orthonormal basis for the tangent space at P. Okay, then all I'm going to do is, so then it has dual basis E superscript 1 up to E superscript 2m. And all I'm going to do is I'm just going to define this top form to be the wedges of all these guys together. Okay. Now, you might complain to me, how do I know this is well defined? Because I've relied on choosing some orthonormal basis for the tangent space. And I'm claiming that this choice, or this formula, doesn't depend on the choice of orthonormal basis you used. So I should make one proviso here. I should say an oriented orthonormal basis. So I did want an oriented manifold here. Otherwise, someone could swap the order of the vectors and I'd get minus that, so that would be a problem. But oriented just means that is a up to scale, the top exterior power, let's just write that down, top exterior power of the tangent space at each point, we know it's canonically, well, not canonically, but it is isomorphic to R. And to say that to have an orientation on the manifold is to choose one of the connected components of. So if you've got something, let's say I've got a function, let's say I've got lambda living inside here, which is non-zero, that means that lambda is living inside R or minus 0, right? Let me write it like this. I know that this can be written as, what's the nicest way of saying it? So if I've got a non-zero vector in the top exterior power, then the top exterior power minus the 0 is going to split into two connected components, right? There's the number 0, but I'm not living in that. So I'm either living in one component or the other component. I can't label it the negative component or the positive component because I don't have a canonical isomorphism between this and R minus 0. Because you have such an isomorphism, you'll have to have chosen a basis. But an orientation is exactly a choice of one of those components, continuous choice of one of those components. Anyhow, that just means that when I'm writing down a wedge product of vectors, I've got to write them down in the right order to make sure that I'm landing up in the right component. Okay. Anyhow, the claim is that on a Kähler manifold, remember, a Kähler manifold consists of a manifold, complex structure, a Riemannian metric, and a symplectic form, and they're all interrelated. The claim is that the Liouville volume form of the symplectic structure is the same as the volume form arising from the Riemannian structure. Okay, so that's just something nice to know. Simplifies your calculations. And we've already seen this in practice because we calculated the Liouville form over here for the two-sphere. How do we calculate it? We use the definition of the associated fundamental form of the metric. So this here is the Liouville form, because if you've got just a two-dimensional manifold, you don't have to raise omega to any power. It's already a top power. So this is the Liouville form. And then we've seen just by inspection that this is also the area form of the metric. I know it's the area form, for example, because if I integrate it over the manifold, I get the area of the manifold. So it is the area form. So that's an indication, or this is an example of that theorem, saying that the Liouville form and the volume form are the same on a Kähler manifold. Anyhow, that is definitely enough for today. Thank you for bearing with me. I'll put the notes up and the YouTube video up.
Awesome, thank you.
For our last lecture, we'll speak about line bundles and how you can construct Kähler manifolds from line bundles. That's a very nice construction. Okay, I'm just reacting to Dario's comment here. In this case, we know it's an area form because we know the area of the full manifold, indeed. But in general, we sort of just have to trust that this is the definition. What quite do you mean by that? Because in general, we're going to have a Kähler manifold like this. That means it's going to have a symplectic form, and from the symplectic form, I could then calculate the associated Liouville form. It's also going to have a Riemannian metric, and from the Riemannian metric, I can calculate the associated volume form of the Riemannian metric. And then the claim is that as long as these guys were all compatible with each other in the sense of being Kähler, then these two volume forms will be the same. So the S2 thing was just, there was only some trust coming in there because you had to believe me that this was actually the volume form. this expression here. But I sort of argued why it was, but just integrating it over the two sphere. But it is the volume form. We could calculate that just explicitly with a little local calculation. Yeah. In fact, let's do that little local calculation. It won't take us long. So we agreed that the volume form is obtained by taking an orthonormal basis and then wedging them together. So the volume form is here's an orthonormal basis here and here. So I've got to take the dual basis vectors. So let's do that. If these are the basis vectors, then the dual basis vectors would be these guys here. So in other words, E theta is equal to d theta, and E phi would be equal to sine theta d phi. Because this guy, when evaluated on this guy, must give me 1. That's why I need this guy will eat up this guy to be 1. Because this guy eats up this guy to be 1, you see? So that means that from this calculation here, we see that the volume form, according to the Riemannian metric on S2, is by definition E superscript theta wedge E superscript phi. And if I write that out in terms of theta and phi coordinates, it's going to be sine theta, theta wedge d phi. So they are proved that it's the volume form of the Riemannian metric.